This is Unit 4, Section 15.3, double integrals in polar coordinates. Suppose we want to evaluate a double integral over the region R where the region R is one of the regions shown in Figure 1. For Figure 1a, if we were going to look at this as a type 1 region, we would have the double integral. Our x limits would be from -1 to 1. Our y limits, the negative square root of 1 minus x squared to the positive square root of 1 minus x squared. F of xy dy dx. For Figure 1b, have the integral from -4 to +4. We'd have the square root of 1 minus x squared to the square root of 4 minus x squared, f of xy dy dx. Now, these get rather complicated, but if we describe them using polar coordinates, the integrals themselves become much easier, and you can see the regions are defined as where the radius is from 0 to 1, and theta goes from 0 to 2 pi. And in the case of 1b, the radius goes from 1 to 2, and the angles go from 0 to pi. So recall from your pre-calculus days that the polar coordinates of a point r theta are related to the rectangular coordinates using the following equations. We have that r squared is equal to x squared plus y squared. We have x equals r cosine theta and y equals r sine theta. So the regions that we showed you in Figure 1 are going to be special cases of the polar rectangle defined as all r and theta such that r is between a and b, and theta is going to be between alpha and beta. Also recall that we know that the arc length of this sector, so this length, is r times theta, and that the area of that sector is 1/2 r squared theta. Now, as we have done with Riemann sums and the double Riemann sums for double integrals, we're going to divide this up into a bunch of smaller rectangles. Now, if we divide this into small enough ones, we can then assume that this actually is a rectangle. And this is d theta. This small change in the radius is dr, and we know that this length of this piece is going to be r times d theta. So then we can say that dA is going to be r times dr times d theta, which then gives us the change to polar coordinates that we're going to, as we see here. So if we have then f of our double integral over region R, and we're in xy coordinates, we can rewrite this over that same region. And remember, x is going to be r cosine theta, y is r sine theta, and our dA is r dr d theta. Now, rather than integrating over that region, we know that r varies from a to b, and theta varies from alpha to beta. Now, this formula says that we can convert from rectangular to polar coordinates by writing in that x is equal to r cosine theta and y is equal to r sine theta, and using the appropriate limits of integration and replacing dA by r dr d theta. Do not forget this extra factor of r on this side of the formula. So a classic method for remembering this is remembering that the infinitesimal polar rectangle can be thought of as an ordinary rectangle with dimensions r d theta and dr, and therefore has area of dA or r dr d theta. So let's go ahead and take a look at example 1. So we have the function 3x plus 4y squared dA, where r is the region in the upper half plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. So our first step is going to be to describe the region, and we are going to write r is all xy such that y is greater than or equal to 0, and x squared plus y squared is less than or equal to 4. And that's the half ring as shown in figure 1b, and its polar coordinates, it's given by where r ranges from 1 to 2, and theta ranges from 0 to pi. So therefore, we can rewrite this integral as, so the double integral for region r, 3x plus 4y squared dA is going to be the integral from 0 to pi and 1 to 2 of 3r cosine theta plus 4r squared sine squared theta r dr d theta. So let's go ahead and simplify that a little bit. We have the integral from 0 to pi and then 1 to 2. This gives me 3r squared cosine theta plus 4r cubed sine squared theta dr d theta. Okay, so we first need to integrate with respect to r first. And so we have the integral from 0 to pi. This becomes r cubed cosine theta plus r to the 4th sine squared theta. R ranges from 1 to 2, and then d theta. So continuing this, we have 0 to pi. This becomes 8 cosine theta plus 16 sine squared theta minus cosine theta plus sine squared theta d theta. And so we now have from 0 to pi 7 cosine theta plus 15 sine squared theta d theta. So we have then the integral of 7 cosine theta becomes 7 sine theta. And remember to integrate sine squared theta, that we're going to use the power reduction formula. So that becomes, we're integrating 15 halves times 1 minus cosine 2 theta. So we are actually integrating, so I'm going to go ahead and move this 15 halves over here. 1 minus cosine 2 theta d theta. So we have plus 15 over 2 theta minus 15 over 4 sine 2 theta that we're evaluating from 0 to pi. which then just gives us simply 15 pi over 2. So what we have done so far can be extended to the more complicated type of region as shown in figure 7. In fact, if we combine formula 2 with, so we have the double integral over region D, f of x, y, dA, and we look at this as a type 2 region, h1 of y and h2 of y of f of xy, dx, dy, we can then come up with the following formula that if f is continuous on a polar region, then we can write this as the integral from alpha to beta and h1 of theta to h2 of theta, f of r cosine theta, r sine theta, r dr d theta.